Okay, so good morning. So let's start the second day. So yesterday, we started with a very fundamental part of the finite element method and 1D code, and including algorithms for iterative method, and also we learned about the method for sparse matrix storage, CRS format, compressed row storage. And the last part of the yesterday, so we started 3D, and so just a moment. Okay, so we defined 3D shape functions. Sorry, 2D functions for this type of the square on the natural coordinate system. And so we have 4 shape functions corresponding to each corner. So this N1 is for this number 1, and this N2 is for this number 2, like this way. And you can see, so it's a xi eta 2D natural coordinate system. And the shape function is 1 over 4, 1 plus minus xi eta. Okay, so I skip this part. And based on the same idea, so we can extend this to the 3D problems. And so tetrahedron or tetrahedra is corresponding to the triangles in the problems. Tetrahedron is also very convenient, and it can handle arbitrary shape of object. And but the linear elements are generally less accurate and not practical. And the higher order tetrahedral elements are widely used. So in the same reasons, based on the same reasons, so we are using the linear hexahedral elements. So instead of the higher order tetrahedral elements, because it's a little bit complicated. But actually, so tetrahedron is very convenient for arbitrary shape. And generally speaking, the most of the real-world finite element applications are based on the higher order tetrahedron, especially for the cases for the structure mechanics. Yeah? But so here we are using the linear hexahedral elements, and it's a so isoparametric element. Okay, just a moment, I should. Okay, sorry. Okay. And this is a shape functions for the 3D natural coordinate system. And in this case, we have a hexahedra, and we have 8 corners. And we have a third axis, it's z, xi eta z. Okay. And you can see, so each shape function consists of the 1/8 multiplied by 1 plus minus xi eta z. Okay. And x and y and z are defined by the linear combination of the shape function, and also this x value at each corner. And the temperature is also defined using the same shape function on the natural coordinate system. And you can see, so they are all same shape functions, and it's a isoparametric type element. Okay, so this is a 3D shape functions, and we are using this one for our application. So, any questions so far? Okay. Okay, so next I'll talk about the 3D heat equations and the Galerkin method and element matrices. So basically, most of the procedures are same as we did in the 1D yesterday. But so we have more data because it's a 3D problems. And you can see, so we have 8 corners here, and it's so 4 times as a so 1D case. Okay, so here we are using the 3D heat conduction, steady state heat conduction problems, and uniform lambda, and we can so specify as this way. And the temperature is n times phi, and n is some vectors of the shape functions, and also temperature is phi is the temperature at each node. Because this is a residual, and we just multiply the shape function as a weighting function here, and integrate at each element. And we apply the 3D Green theorem for this part. And so yeah, you can see, so in order to save the space, so instead of writing in this way, so I write the second order differentiation by this way, so gamma xx. Okay, so you can see, so these are so 3 terms for the partial differentiations. Okay, and so n is a here, and t is b here, and you can see, so this is the right-hand side of this Green theorem, and so here we have already canceled this so surface integration. So because as I mentioned yesterday, so this part is some so heat flow through the surfaces with the neighbors, and this part is canceled to each other. So we don't need to so think about that. So at this stage, I have already so deleted this one. Okay. So you can see, so this left-hand side can be written in this way, okay? So T is n phi, therefore the partial differentiation of the T by x and y and z, those for n, okay? So yeah, because the phi is some certain values, and n is a so function of x and y and z. So they are differentiated by x and y and z. It's also same as a 1D case. But now we have so 3 terms in each direction. Okay, so finally, so this is a weak form for the 3D case. And you can see, so we are multiplying the first order differentiation by x and y and z for shape function, and it's transposed. Okay, and this puzzle is corresponding to the heat generations. So in this case, we just multiply the n and provide the integrations. Okay, so this part is the same as I showed yesterday, but I repeat. So this is called weak form, and the original PDE consists of terms with second order differentiation. But this weak form only includes first order differentiation by Green theorem. Requirements for shape functions are weaker in weak form, and the linear functions can describe effects of the second order differentiations. The same as 1D problem. Okay, so this is our target so equations now. Okay, so we are so discrete so making the same so procedures, and so this is a so-called element matrix, and this is the element temperature, and this is a right-hand side. So this K is defined as the sum of these 3 terms in x and y and z direction. In the case of the 1D, so we only consider this x direction. But because this is a 3D, we need to think about that. So y and z. Okay. And this one is so right-hand side, it's based on the heat generations for each element. Okay, and 1D case, our element matrix was 2 by 2. Okay, we have 4 components. And in the case of the 3D, so we have 8 corners, and the element matrix is 8 by 8. Okay, so it's a very large or larger matrix compared to the 1D case. And so this ij component in ith row and jth column, we call this a kij. So we have 64 such components. Because this is a definition of the matrix K, and so definition of the Kij is defined as this way. Okay, and this one was a 1D case, and this one is a 3D case. Okay, so because this one is corresponding to the I, because it's derived from the weighting function, and this is corresponding to J components. So this is derived from the each corner. Therefore, so we just multiplying the Ni and Nj, and differentiate by X and Y and Z. So yeah, we are multiplying this way. Okay. So this is a component of this element matrix, and it's defined by these integrations. So lambda, Ni and Nj, so differentiation by X, and the same for the differentiation by Y and by Z. Okay, so we are multiplying these two terms and add these three components. Okay, so this is a very brief overview of the definition of the element matrix. The next step is how to calculate this integration. Okay, so any questions so far? Okay, so numerical integration is one of the very important area in the mathematics or applied mathematics, and I believe there are still ongoing works, and yeah, there are many researchers in this area. Yeah, I believe some of you have already learned about the very fundamental numerical integration, such as a trapezoidal rule, or Simpson's rule, or Gaussian quadrature, or Gauss-Legendre integrations. The last one, Gaussian quadrature, is a very accurate method, and also it's very feasible for the natural coordinate system. So in this, generally in the finite element case, we use Gaussian quadratures. The idea of this type of the numerical integration is values of functions at finite numbers of sample points are utilized. So generally speaking, if we do the integrations, we are thinking about some continuous function fx, and from x1 to x2. But instead of that, so we just digitize or sampling the several values of the functions at certain points and multiply some weighting factor. Then take a summation. Then we can approximate this type of the integration. In order to do this, so you need to know the analytical integral form. But in the case of the numerical integration. You don't need to know that. Okay? So it's more convenient. And so generally speaking, so these methods are very accurate. Okay, so let's think about two types of method. One is the Simpson's method, and another one is the Gaussian quadrature. And think about the integration of this fx equals sine x between 0 to 0.5 pi. Okay. And you know the result, analytical result is 1 for these integrations. And so in the case of the Simpson's method, we need at least 3 points. Okay? So then take 3 points. 0, so quarter pi and half pi. Okay? And h is so this mesh size, and it's equal to 0.25 pi over 4. And according to the Simpson's rule, so integration is calculated by this way, okay? Using these 3 points. And the result is 1.0023. So you can see it's a very accurate, okay? And the error is roughly 0.2%, even if you only use 3 points. So in the case of the Gaussian quadrature, we need some transformation of the coordinate system into the something like the natural coordinate system. So between -1 to 1. So in the case of the Gaussian quadrature, we can start for just one integration point. But here we are thinking about the 2 integration points. Okay, and so this is the 2 points, and if we transform this 0 and pi over 2 into the -1 to 1, these 2 points are plus minus 0.57735, something like that. Okay. And if you want to do these integrations from 0 to so pi over 2, the corresponding so integration is -1 to 1, and so this so f so theta. H is so this mesh size. Okay, and so finally, so we have 2 points, and so value at each point, and multiply so this weighting factor, and the result is so 0.99847. You can see they are very accurate. Okay, just using 3 points or 2 points, and this one is a little bit more accurate. So yeah, very small. And so anyway, so this Gaussian quadrature is a very feasible for the natural coordinate system, and we use this one for this class. Okay. So Gaussian quadrature is a normalized natural or local coordinate system between -1 to 1. Okay, it's a natural coordinate system or local coordinate system. Okay. So it can approximate up to m-1 order of functions by m quadrature points. Okay. So therefore, m equal 2 is enough for quadratic shape functions. Okay. So actually, in the case of the linear so element, m equal 1 is okay, but generally speaking, m equal 2 is used. Okay. So basically, so idea is a -1 to 1, and so this is a function of Guzai, and we calculate the integration at some sampling point and multiply by some weighting factor and the sum of these. Okay. So I just show you the 3 cases: m equal 1, 2, and 3. Okay. M equal 1 is very easy. and sampling point is here. It's a midpoint, and so weighting factor is 2. Okay, because so this is something like a average values, and so we just multiply by 2 to get the actual values. N equal 2 is a very widely used one, and as I mentioned in the previous page, the 2 points are plus minus 0.577 or something. And the weighting factor is 1, so just multiply 1, okay? And the n equal 3 is, so we have 3 points, 0, and plus minus 0.774497. And we apply the different so weighting factor here, okay, like this. So I show you the case for the m equal 2, because it's a plus minus 0.577, and it's a little bit outside of the, so between the -1 and 0 and 0 and 1, okay? So you can see, so these are the 2 sampling points. Okay? And we can easily extend this idea to the 2D and 3D. So this example shows a 2D case. And so this is corresponding to, we have 2 points, okay? And in the case of the 2D, we have 4 points, okay? And the coordinate of the, so these 4 points are plus minus 0.577 something, as I mentioned before, okay? And in this case, so we multiply the 2 weighting factors in each direction, okay? In the case of the m equal 2, the weighting factor is 1. Therefore, this doesn't matter. Okay. So anyway, so this is a 2D case. Okay. Yeah, this is how we calculate the this 2D case. Okay. Because we need to do the integration from -1 to 1 for xi and eta. Okay. And this is a definition of the integrations. So in this case, so coordinate of the point is a plus minus 0.57735. And so weighting factor is 1 for all cases. And we have a 4 terms here, okay? So everything is multiplied 1 and 1. So this part is, doesn't matter. And we are multiplying the function at minus and minus, and minus and plus, and the plus plus, and the plus minus. Okay. So basically, so we are adding the values at these 4 points, okay? Because the multiplication value is 1. So this is how calculate the integration. Okay. So any questions so far? Yes, so generally speaking, so m equal 2 is okay. And so even if you use a very higher order interpolation function, yeah, it works. But so if you are trying to use finite element method for the structural mechanics, so it's we need to be careful about that, because sometimes this type of the many integration points provides a little bit hard result. Okay, so for example, if you have this problem, and yeah, you can calculate the deformation by some force in finite element method. But so if you apply this type of the very so dense integration point, the result is a little bit harder than the so actual result. Okay? Harder means so definition is small. And this is a very well-known problem. And in that case, this situation is improved if you use so just 1 point for the integration. And this is a very well-known technique as a so reduced integration. If you are trying to use finite element method for the structure mechanism, so you should think about that. So actually, I mentioned that about the Nastran. It's a very widely used general purpose commercial code for so structural mechanics. So they provide several kinds of the element. So one is this type of the full integrations, and just 1 point, they call that reduced integration. So we can choose such element. But anyway, so these are the out of the scope of this class. But generally, so this one is okay for many types of the so elements and problems. But if you are working for the structured mechanics, so you should be careful about the selection of the integration point. Does it answer your question? Yeah. Okay, so this is a 3D extension. So I have no 3D figures here. But in the case of the 3D, so we have so triple nested integrals and triple nested sum. And we need to multiply the 3 weighting factors. Okay. Okay. But anyway, so this Wi and j and k are all equal to 1.0, and you don't care about that. Okay. So this is a so 3D case. Okay. Okay. So next one is some partial differentiation on natural coordinate system. So according to the formula of the analytics, so differentiation of this step function by xi and eta and z are defined in the this ways. Okay. So actually, so n is a function of xi, eta, and z. Okay. But it can be described as a multiplication of the two terms. And so n differentiated by x, and x differentiated by xi. Okay, so this one is y, and this one is z. Okay. And you can see, so we have two types of terms. Okay, one is a differentiation on the original coordinate system, and this is some differentiation between the original coordinate system and natural coordinate system. And if you go back to the matrix, we need the differentiation by x and y and z. But so n is a function of the xi and the eta and z. And you can see, so these terms can be easily derived according to the definitions. Okay? So because it's a function of xi, eta, and z. But we need these terms. Okay? And so what should we do? So if we write these equations in the matrix vector multiplication system, it's written in this way. Okay? And left-hand side is a differentiation by natural coordinate system. And so this is a 3x3 matrix, okay, and by vector. And the vector part is a differentiation by x and y and z, okay? And you can see, so this 3 by 3 matrix is very interesting one and a very important one. So generally it's called Jacobian or Jacobi matrix. Okay. And you can see, so upper part is x and y and z, and the lower part here are xi and eta and z. Okay. We have a x and y, x, y, and z, and xi, eta, and z. So we have 9 combinations. So it's corresponding to each pair. Okay, so this is a Jacobian matrix. So this J11 to J33 is corresponding to the each component of this Jacobian matrix. Okay. For example, this one. So dx d eta x differentiated by eta. Okay. Because x is defined in this way. Okay. So linear combination of the shape function and x. So we just differentiate this by eta. Okay. So x is a certain value, and so n is a function of the location. So therefore, so this second J21 is defined as this one. So linear combination of the x and so n differentiated by eta. Okay. Yeah, we can apply the same rule for the other part. Because n is a known function, and x and y and z are all known values, and we can calculate each component of the Jacobian matrix. Okay. So therefore, if you multiply the inverse matrix of the Jacobian to this right-hand side, so you can get this target functions. Okay. So partial differentiation on global coordinate system. This one is introduced as follows with the inverse of the Jacobian matrix. So this one, 3 by 3. Okay, to make it clear, so this is each component of the element matrix Kij, and we are going back to this method for writing. Okay, so we have 3 terms, and each term is corresponding to Ni and Nj differentiated by x and y and z. Okay. Okay, so this is a target integrations. And so this dv is corresponding to dx, dy, dz in 3 directions. Okay. And finally, so we need to do this on the natural coordinate system, because so the parameter is changed from dx, dy, dz to d xi, d eta, dz. And we need to multiply the determinant of the Jacobian matrix here. Okay. So thus we can calculate the integration of this, and we can apply the Gaussian quadrature for this part. Okay, this one. And this part is corresponding to this f. Okay, so these 3 terms multiplied by determinant of the Jacobian. Okay, and so we can calculate using this one. Okay, so remaining procedure is element matrices have been formed, and so accumulation to the global matrix is needed, and the implementation of the boundary conditions and solving the linear equations. And the details of the implementation will be discussed in the classes later than this slot. Okay, through the explanation of the details of the code. Okay, so I'll talk about the details of the implementation in the later stage. Okay. Yeah, in the case of the 3D element, we need a little bit special treatment like this way. So in the case of the linear tetrahedra, we can do the analytical integrations as we did in the 1D case. And it's much easier. But so in the case of the hexahedra, and also the higher order tetrahedral elements, we need this type of the numerical integration. Okay. Any questions so far? Okay, so we can do the same type of the accumulations. So in this case, we have only two 2D elements and a 4x4 element matrix, and we accumulate this way. So in this case, it's not so sparse, but so if we have many elements, we also have the sparse matrices. Okay, so before going to the actual program, so let's do the exercise. So in order to understand the Gaussian quadrature, okay? Yeah, please develop a program and calculate area of the following quadrilateral using Gaussian quadrature. So this is a target quadrilateral element, and these are the coordinates. Okay? And you can easily calculate the area by the some analytical way. But please use a Gaussian quadrature. So corresponding value is this one, and so what you have to do is just calculate the determinant of the Jacobian matrix at each quadrature point and do some calculations. Okay. Okay, so this is some Fortran sample, and so we have we are applying this case, and we have two types for the weighting factor, and two types for the points. Okay, and we need to calculate total values, and we have two loops. So one is IP is corresponding the Xi directions, and the JP is eta directions. And the value is function at these 2 points. Xi and eta point. Yeah. And what we need to do is sum of the WIP and the WJP multiplied by FC. Actually, W's are all 1, and yeah, you just add the 4 values for FC. So this is what you have to do. Okay. And so next page shows a corresponding Jacobian matrix in 2D case. In the 2D case, we have just 4 components. And the determinant is very easy to calculate. So you just calculate some AD minus BC. So this is a determinant. Okay. Now these are the how we define the Jacobian matrix. Okay. And this is a shape function. Okay, so now it's a 9:50. Okay, and so yeah, let's do the exercise, and you can you need to make some program. Okay, for or C, but it's not so difficult. Okay, and so I think I should give you the 30 minutes, including break. And so at 10:20, we will start the next lecture, where I will explain the detail of this exercise. Okay, so please start. And you can take a break, so if you like. Okay, so let's restart. So has anyone made it? Raise your hand. No? Okay. Okay, so, okay, be back to the, yeah, if you go to the home page and click the FEM part, and you can find this homework too. I show some examples, okay? And so I just briefly introduce this part. Okay, so this is some overlap with the original class materials. And this is so problem. And this is some tips which I mentioned. Okay. Okay. You know the answer because so if you write in this paper, you can easily calculate the values. And also, according to some so formula, you can also calculate this value. So result is 6. Okay. Okay. So final target is so these integrations, just so integration of these values for the 2D elements, and on the natural coordinate system. So what you have to do is so calculate the integral in this so surface from -1 to 1, and just calculate the determinant of the Jacobian. Okay. And so this is a Gaussian quadrature formula. So you need to multiply the weighting functions. And f is a determinant. And so what you have to do is a view of the determinant at each point. Okay, so that must be calculated. So which is this one. So Jacobian xi I eta j. Okay, so I just show you the very small examples. It's a program, but it's very simple. So what it happens. Okay. And so you can easily write in other language. Okay. So first you define the okay, x and y. And also we define the weighting factor and position of the quadrature point, plus minus 0.577 something. Okay, like this way. And the next one is defining the value of the shape function. And so first order differentiation by xi and eta of the shape function at each quadrature point. Okay. And you can see this O is a 0.5. It's corresponding to the 1 frame. Okay. And so you can see we have WNST loops in each direction. So you can see QP1, QM1, EP1, and EM1. Q is corresponding to xi, okay? E is corresponding to eta, okay? And the P1 is a +1, and M1 is a minus, okay? And you can see, so QP1 and QM1 is a 1 plus minus IP. So post is the position of the quadrature point. And the EP1, EM1 is a 1 plus minus post JP, okay? Because the IP is in xi direction, and the JP is in the eta direction. So thus we define these values here at each quadrature point. So next part, we calculate the value of the shape function. 1, 2, 3, 4 is corresponding to N1, N2, N3, N4. So next part is calculated partial. So what is partial differentiation of the n and n for the by the xi and eta. Okay. So actually, so if you apply the differentiations, so this index is decreased by 1 this way. Okay. And so yeah, so they are calculated. So actually, so these are the actual values for the so if you differentiate by xi, so you can see only one term related to eta is remained like this way. Okay. And in the case of the differentiation by eta, we only have the terms for the xi like this way. Okay. Okay, so what we have to do next is calculate the value of the determinant of Jacobian at each quadrature point. Okay, so in order to do that, so you need to calculate each component of the Jacobian. Okay, so there, so dx dq is so dx d xi. Okay, and dx d is dx d eta. Okay. And each term is calculated by this formula. And because we have already calculated this value in the previous page, and we just multiply by value of the coordinate x and y, and so sum of the 4 terms, okay, like this way. Then we calculate the determinant at each quadrature point. And finally, so we have to do is visiting a 4 quadrature point. And so this determinant value is multiplied by weighting factor WYP and WJP. So both are. So that means we are just summing the value of the determinant at each point. So this area is the answer. And this one is some analytical solutions. And we can compare the analytical values and so Gaussian quadrature result. Okay, so this is just, so it's a little bit complicated, but you can do the numerical integration in this way. And we just follow the same procedures in the actual finite element method. Okay. Okay, any questions for this part? Okay. Is that okay? Well, I think I should be away from this speaker. So this means I should use this one. Okay, so let's go back to the 3D finite element part. And okay, so before going to the details of the program and data structure, so let's run the code itself. Okay, and so this is the program definition, and so this is how you install the code. Okay, and please go to your directory. directory and go to this SRC directory and type make. And you can find the same file in the directory of run. And the next one is going to the run directory and compile the this mesh generator. Okay? And generated with the MG cube. Okay. Yeah, so please do this. So this is on your PC. Okay. So go to the FEM3D and go to the SRC. And type make and go to the run directory. And so CC is okay, I think. O mg cube.c minus O mg cube. Oops. So please make sure Sol and mg cube is created, okay, like this way. So my PC is according to Japan standard time, so it's 1 hour ahead. Okay. Any problems for this part? Okay, so this is the operations for the 3D case. So in the 1D case, we generated the mesh inside the program. In the 3D, it's a little bit complicated, and we have a separate mesh generator. Okay. And MGQ creates a cube.0. It's a mesh file. It's a fixed name. And the sol is a finite element solver. And the input data, it's a control data. It's a fixed name. And they are reading these two files and calculate. And finally, output the test.in. It's also the fixed name. And this is for the visualization. Okay, so let's generate your mesh. Okay. And please go to the run directory and type /mg cube is okay. Okay. And you are asked to enter mesh number in X and Y and Z directions. So you type 20 blank, 20 blank, 20 and return. Then you can create cube.0. Okay. So please do this. Oops. So you can get the cube.0 and type it like this way. The top one, 9261, shows the number of the nodes. Okay, it's a number of vertices. Okay, element number is 8,000. It's more than Actually, it's a any one cube, okay, like this way. Oops, it's happening. So if you have create the file, so you can see the content of the input that, okay. So it's a very simple file, and the first one is the name of the mesh file. So cube.0 is a fixed name, and the 2000 is a number of iterations for the conjugate gradient method, and that, yeah, 2000 is enough. And the one, so there's a conductivity, and so this unit heat generation values. And the last one, 10 to the minus 8, is a criteria for convergence of the conjugate gradient method. Okay, so if you check the content, this part is okay, like this way. So then type the sol dot slash sol. Okay. Just okay, so it's calculated, and so it means it needed 61 iterations for convergence. Okay, and the last value is some so oops, this is not that. Yes. You can see. So this is so some history of the convergence. And the last value is 1 and so 3,391 something. So this value is a temperature at the origin 0. So actually, so this is a very big value, but so you don't mind about that. So this provides a value at this origin. Okay. And in the later stage, so you will do the parallel computing. Okay. And actually, if you apply some kind of the parallel computing, so results may change if you have some bugs. Okay, if you have a program, so it remains the same result. But if you have any so wrong implementation, so it provides a wrong answer. And in order to check the validity of your coding, so it's very helpful to check the values at this point. Okay. Yeah, of course, the parallel computing is for the performance. But so as I mentioned, so yesterday morning, the scientific computing includes science. Okay, so this is a very simple science, but so answer and accuracy is very important. So please, so take care of that. Okay, and test.inp is written, and you can browse by paraview. Okay, and you can see some instruction on the website. But yeah, you have already installed your paraview, and it's better to run now. Okay, just a moment. Oops. Okay. So you can see you have a test.imp here, and so you can open the view. Takes the time. Okay, so this is a Paraview window, and you can open your file. And you can go to your some, directory and find your desktop imp and click this. And you have several selection, okay? And please select this AVS UCD reader. In the old version, so this appears in the second item, but so please use this AVS UCD reader. Okay, so in this case, it's the first one. Then type OK. And so after that, so please click this apply, and you can get the result like this way. Okay. Actually, so I have already shown this yesterday, and you can see. So this is a surface, and the temperature is 0, and it's going higher and higher in the direction of the bottom. And this is a origin because you can see this so 3 axes. Okay, and you can see so this part is a little bit lower compared to this diagonal opponent. So if you don't like this color, I think you can change this. Okay, so this one. So if you find this some hard mark, it's a choose preset. And so you can change some colors. And I think, yeah, for example, this rainbow uniform and apply. And go back to the original window. And you can get a more colorful ones. Okay. But you can rotate the values like this way. And also, you can save the snapshot of the screen by this save screenshot. Okay. And you can save as a JPEG or a bitmap, PNG or PDF or other format. Okay. So, for example, and how about the test.jpg? And so, okay, and yeah, they ask some parameters, but so yeah, you can just go to the default. Then you can save this as a JPEG file. And so if you go to the target part, yeah, you can find this JPEG file like this. Okay. Yeah, if you write some report, yeah, it's very useful. Okay, so did you try this? Any problems for? Okay, you can write. So anyway, so it's very useful tools, and please, yeah, play with this. So I just briefly describe this Paraview, and the file is based on the UCD format. So UCD stands for the unstructured cell data, and it can handle arbitrary shape from 1D to 3D, including the higher order element like this. And in this case, we are using this linear hexahedra. Okay, it's a hex. Okay, so this UCD format was originally developed for AVS or micro AVS. So they are some very well-known visualization tools. Okay? And the extension of the utility file is INP. And so in this case, it's a test.inp. So if you want to use this UCD format, the file must be .inp. So there are two types of the formats, and only all types can be read by reviews. So therefore, my file is written in the old format. Okay. And I skip the detail of the format, and if you are interested in, so you can go to the paraview.org or just a Google UCD format. Okay. Okay. So this is how to run the code, and it's very interesting. Yeah. So next, so I'll talk about the details of the cube.0. So it's a mesh file data structure. So it consists of several groups. One is about the nodes and the elements, and also the node groups where we apply the boundary conditions. And each group includes a number of nodes and node ID and coordinates, or element number, element type, and element ID, material ID, and connectivity. So connectivity means information about the nodes which provides each element. So node groups is a group number, nodes in each group, and group name, and nodes in each group. So this is a node number in each group. Okay, so I will show you the details. The current value, so we have 8,000 elements and 8,000 elements and 9,000 nodes. It's a huge. So let's think about the smaller number of meshes. Okay, so this is a 4x4. Okay, like this very small mesh. Okay, and so you can create this type of mesh on your PC and the MG cube and 4x4x4. Then you can get the cube.0 like this way. So it's a very small files like this. Okay. Yeah, like this. Okay, so next, so I just show you the content of these files. Okay, so this page shows the first part of this cube.0. And this part includes information about nodes. Okay, because we have 4x4x4 meshes in each direction, and this means 5x5 nodes in each direction. So therefore, we have 125 nodes. And after that, so we have information about the 125 nodes. Okay, and so first column shows the node ID, and these three numbers are coordinate in 3D coordinate system. The first node is origin, and the first we generate nodes in x direction. Okay, you can see 1, 2, 3, 4. Then we go back to this one, and we generate the mesh in y direction. Okay, so finally we generate the mesh in z directions, and you can see the last one is a 4, so corresponding to this one. Okay. Yeah, this is how we generate the mesh. And the next part shows element information. And we have 64 elements. And so we have 361. And you can count. We have 64, 361. So this 361 shows element type. Actually, in this program, so we have only one type of element. But so if you can think about the extension of this program. So in that case, we can include multiple types of elements. So this is another merit of the finite element method. So in this case, all the elements are hexahedral mesh, and we just describe the type of each element. So 361 means a 3D hexahedron, so 6 surfaces, and the linear first order. Oops. Okay, so next one is sorry. So next one is information about each element. Okay, and we have 10 integers. And the first one is a element ID. So it's a continuous number from 1 to 64. So next one is a material ID. So we have only one material. So every material ID is equal to 1. So next 8 numbers are corresponding to the node ID for each element. Actually, so node ID for each element is numbering in this way. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And if you go to the first element, so it's a 1, 7, 6, and the 26, 27, 32, 31. Okay. Because we have 5 nodes in the first line. Okay. Therefore, this one is number 6. And we also have the 5 nodes in this first layer of the surface, and this one is at 26. Okay, so thus we generate the element. Okay, so next page shows so number ID of element. So these are red letters, and these black letters are showing the ID of the node. Okay. So this is the first layer, second, third, and fourth, and fifth. Okay, and you can see so this so the first element is a 1, 7, 6, and 26, 27, 32, 31. Okay, like this way. Okay. The last part is so node group. Okay, so it's very convenient for specifying the boundary condition. Okay, and the first value is 4. 4 is a number of groups. And in this case, we have 4 groups. So basically, it's a X minimum, Y minimum, Z minimum, and Z max. Okay, we just use the last one. And the next one, 25, 50, 75, 100. So 4 numbers here. So this is corresponding to the number of groups. And this is a number of nodes in each group and accumulated values. So this means first group includes 25 nodes, and the second group includes 50 minus 25, so 25 nodes. And the third one is also 25, and the fourth is also 25 nodes. And then we have 4 groups here, and the first one is name, and the next one is ID of the nodes in each group. So as I mentioned, so in each group, so we have 25 nodes, and it's included in each part. For example, this Zmax. Zmax is this top surface where we specify the Dirichlet boundary conditions. And if you go back to the previous page, the top surface is from 101 to 125. So we have 25 nodes. And if you go back to the, so yeah, you can see, so Zmax is 101 to 125. Okay. Okay. Actually, so mesh generation is a very big technical and research issues. So especially for the complicated geometry and large scale case. Yeah, actually, analyzation is difficult, and so yeah, it's still a very uh, difficult things. So there are several commercial mesh generator, and so yeah, large scale mesh generation is still a big issue. And I think we have some rubies here. Okay, so this is a this is a very old mesh, and actually, so this is a very structured mesh, and it's some electrical device, and so it's a combination of the several types of the small models, and yeah, this type of mesh can be generated very easily by the commercial mesh generator, but this is a very simple case. Okay, so this is a very brief overview of the Cube.0 data structure. So any questions so far? Okay, if not, so let's go to the next part. It's a content of the 3D code, okay? And basically, structure is the same as we did in the 1D case, but as I mentioned, codes are a little bit longer because the information for each element is much larger than the 1D case. So that's why we have more information. But the structure of the program is the same as before, starting with the initialization and generation and assembly of the matrix and solving the linear equation. Yeah, because we have a little bit longer code. Yeah, in this case, we have functions and also subroutines. Okay, so test one is the main part, and we have several functions here. Okay, and the first two are input control and input grid. So they are reading input dot and Cube.0. Okay, like this way. Okay, so you can see, so last part is writing the result at origin. So this table describes the global variables, and it's described in the pfm util edge. Okay, so fname is the name of the mesh file. It's a Cube.0, and np are node number. And isl dot is the element number, and node group dot is a number of node group. And XYZ is a 2D coordinate, 2D arrays. So it's a node coordinate. Okay, so we have a XYZ information. So isl node is a element connectivity, and so you can see, so we have 8 nodes for each element. So that's why we have this type of structure. And the node group index and the node group item is a number of the nodes in each group and the node ID in each node group. The relationship between node group index and node group item is similar to the CRS format. So index and item, which I mentioned yesterday. And the node group name is name of each node group. Okay. So NMU is I'll show you later, but it's a number of non-zero orbital components at each node. And NPLU So NPLU is a non-zero dynamic components number. And the B and X are some vectors, and size is n, and the diagonal component of the quotient matrix. And the B is the right-hand side, and the X is an unknown vector. And the A-mat is a non-zero dynamic components of the global matrix, and the size is NPLU. And you can see so index LU and the item LU are the CRS format. And then we have a new arrays INLU and IALU. Okay, so INLU is a number of non-zero dynamic components at each node. Okay, so this is sizes n. So IALU is a column ID of the non-zero dynamic components at each node. Now you can see, so this is a n by NLU. So NLU is defined in the previous page here. So actually, INLU and IALU are corresponding to the index LU and item LU. And so basically, so these two are some intermediate or auxiliary information. So this one is work arrays, and so these are the some number of iterations and the convergence criteria. And this PFM-I array and the PFM-R array are the some parameter arrays or integer and real number. So real number is double operations here. Okay, so this is a last one, and this is corresponding to the some numerical integrations. So pH is a 1/8, so 0.125. And the PNQ, PNE, PNT is a, so this is a, so partial differentiation of the shape function by xi eta z at each Gaussian quadrature point. Okay, so that's why it's a 2 by 8. 8 means the number of the shape function. And the constant way so coordinate and weighting factor at each Gaussian quadrature point. And so these are some work arrays for sorting. And you can see shape is so value of the shape function at each Gaussian quadrature point. Okay, so we have 8 points, and 8 is a number of the shape functions. And also we have another so partial differentiation by x and y and z. Okay, they are Pnx, Pny, Pnz. So they have also these so total 64 components. So J is a determinant of the Jacobian matrix at each Gaussian quadrature point. And the cond and q are thermal conductivity and heat generation rate. Okay. Okay, so I'll talk about the so details in the so next part. I think it's better to take a break. Okay. Okay, so let's have a 5-minute break. Well, no, 7-minute break. Okay, and we start at 11:10. Okay. Okay, so good afternoon. So let's start the afternoon session. Okay. So before going to access a parallel computer, we start from the introduction to the parallel finite element method. Okay. So you have learned about the finite element method in these 2 days. And before going to the more detailed so parallel computing issues such as OpenMP and MPI, I will show you some grand design for so parallel finite element applications, focusing on the data structure. Okay, so this is the motivations and so parallel computing, which I mentioned yesterday, and faster, larger, and more complicated. And I have already talked about the scalability. One is so weak scaling, and another one is strong scaling. So in this class, we are mainly focusing on this part, solving a problem so fixed size of the problem using n times computational resources during 1/n computation time. Okay. So this is for the faster computation. So basically, so parallel computing is solving the larger problems faster. Okay. So this is a sample of the mesh for the granddaughter simulations provided by Lawrence Livermore National Laboratory. And so this is a very homogeneous models. And if you see the actual underground model, so you need to do this type of very heterogeneous models. And so very fine meshes are required for simulations of this type of the meshes. And also this type of the distribution of, so this case, water conductivity is something like the thermal conductivity is a heat transfer is very heterogeneous. And it's also stochastic. So it's very difficult to find some deterministic single model. So that means you need to solve the large number of the parameter studies. And you also need large scale computers. Okay, so yeah, currently most of the PC has a 4 gigabyte or 8 gigabyte, but if you think about the 1 gigabyte of the memory, and 1 million meshes are the limit of the finite element method. So this means a nonlinear practical finite element method. Okay. For example, if you solve the problem for the earthquake simulations for the Southwest Japan with a 1,000 kilometers square and 100 kilometer depth using the 1 kilometer mesh. Okay, so 1 kilometer mesh is a very coarse mesh, but even in this case, you need over 100 millions of meshes, and you need you think that so single CPU is not enough. Okay, and in order to solve the large problem, so we have a large scale data, and we need to do some domain decomposition. Okay, and we decompose the large scale data in the small chunks, and we apply the local operations. So this basically local operation, parallel computing is a local operation. But in order to keep the global consistency, we need inter-domain communications. Okay? So this is a original large-scale data. Yeah, you can consider this a large-scale mesh for finite element method. When you need to do partition into the small local data, in this case, there are 4 regions. Okay, and we apply the local computing for the local data. But actually, this is originally a single large-scale data, and in order to keep the consistency, so you need communication. So that's the procedures of the parallel computing. So as I mentioned, basically computing is equal to the local operations, and communications are required in global operations for consistency. Okay, so next page provides operations in finite element method or parallel applications based on the SPMD. SPMD stands for the single program and multiple data. Okay. So large scale data is partitioned into the distributed local data set like this. So it's local meshes. And so finite element code can assemble coefficient matrix for each local data set. So this part could be completely local and same as serial operations. So if you remember the operations of the matrix assembly part, so that part is based on the element by element computations in each element. So we do the configuration of the element matrix, then accumulate that to the global matrix. So basically, this part is done so totally parallel manner. But finally, you need to solve the linear equations by linear solvers. So in this case, it's a we can use conjugate gradient method. And in that case, we need some global operations and communications. Okay, but this type of the communication only happens in the linear solver. Okay, so dot product or matrix multiply and certain kinds of the preconditioning method. But basically, so you can do the finite element procedures in very parallel and local manner. Okay. So anyway, so you will learn about more about that in the coming couple of days. Okay, so this is the procedures of the SPMD. So basically, so single program means so in each process, same program is running. Okay, so basically same program is running, but the data is different. Okay, and each process does the same operations for different data. And large scale data is decomposed, and each part is computed by each process. And it is ideal that parallel programming is not different from serial one, except communications. Okay. And so this is very important here to understand the parallel computing and also the operations of the MPI. Okay, it's based on the SPMD, or single program and multiple data. So as I mentioned in that corner, so you understand 90% of MPI if you understand this figure. So I showed this figure many times during this week. And please grab this idea. So the same program is running on each processor, but different data. Okay. So parallel finite and the procedures, to design on local data structure is important, as I mentioned yesterday morning. Okay, for SPMD type operations in the previous page. So especially matrix generation part and the preconditioned iterative solvers for linear equations. So they are most expensive part in the finite element method. And so designing the data structure for these operations is very important. Okay, so let's think about this type of the 3D elements. Okay, so data size is very small, only 3 elements and 8 nodes. So let's think about dividing into 2 domains by node-based manner. So that means a node number is balanced in each process. But local information is not enough for matrix assembly. For example, in this case, the information for the number 2 mesh is missing. And so the corresponding matrix information for this number 2, 6, 7, and 3 are not created. So basically, we have some shared this number 2 mesh, but this partition and this partition, we can generate the proper matrix information. Okay. So this is a fundamental idea for the parallel finite element. So this type of the boundary elements are shared by both parts. Okay, I think Okay. Okay, so this is very important for towards Society 5.0. So Society 5.0 is proposed by Japanese government. Okay, and it's a super smart and human-centered society by digital innovation such as IoT, big data, AI, etc., and by integration of the cyberspace and physical space. So you may have heard about the digital twin. So you can see integration of the cyberspace and physical space is the idea of the digital twin. And so we started BDEC project. So BDEC stands for the Big Data and Extreme Computing. So it's a platform for integration of the S plus D plus L. But here we are focusing on the simulation. Okay, and so this S part is very large. And this idea is called AI for HPC or AI for science. Okay, and this plan started in 2015, or 8 years ago. 2 years ago, we started the operations of the Wisteria BDX11, so which you are using now. Okay, so this is the first BDX system and the platform for integration of S plus D plus L. And the total peak performance is 33 petaflops, and the aggregated memory bandwidth is 8.38 petabyte per second. So this is by Fujitsu. Okay, and we have two types for the node groups. And one is called simulation nodes, and the name is Odyssey. And it's Fujitsu's Prime HPC FX1000, and based on the A64FX. And so this is a commercial version of the Fugaku supercomputer. Okay? And the total peak performance here is 6 petaflops, and we have nearly 8,000 nodes. Okay? And another part is data and running nodes called Aquarius. It's for the data analytics and the AI machine learning workload. So it consists of the Intel Xeon Ice Lake processors with the NVIDIA A100 GPUs. So totally we have 360 GPUs, and the peak performance is 7.2 petaflops. And some of the this Aquarius part are connected to external resources directly. Okay? So this is a ranking, and so this is a little bit old one. So now the Odyssey is 25th in the world. Yeah. So this is how we utilize this system. Yeah? Because we have a Odyssey part and Aquarius part, and so real world simulations are they are non-linear, and we need a lot of parameter studies, and in order to optimize models and the parameters, we utilize external observational data or some machine learning. So in order to accelerate the optimization cycle with the parameters and the models, so we utilize this part. So this is an ideal way for utilize this system. But in this school, we just use a small part of this Odyssey. So this is the hardware, and we are also developing the software to develop the efficient software applications on this platform. So this part is supported by Japanese government, and so actually it started 4 years ago, and we are now in the last year, final year of the 5-year project. So PI is myself. And there are 3 innovations. One is a new principles for the numerical analysis by adaptive precision, automatic tuning, and accuracy verification. It's a utilization of the low precisions or mixed precision. So next one is the integration of the machine learning and simulations. I skipped the detail, but so this is a summer. Utilizing the adaptive precision part. So the double precision is a FP64, and single precision is FP32, and half precision is FP16. And we developed new precisions, FP21 and FP42. So they are between these half and single and double. And it's very efficient, and also it's very robust. Another part is the integration of the machine learning and the simulations. So this one is try to predict the transient computations by machine learning. So, but in the very slow flow, it's possible. But if you apply the very high range number fast flow, a little bit difficult. But anyway, so it was successful in certain kind of the applications. The third category is software and utilities for heterogeneous environment, such as Wixter BDX01. And the Wixter BDX01 is the first really heterogeneous system in the world. And so we need to develop a software to connect these components. Okay, so I think I can skip this part. Okay, so I think, yeah. MP is a multi-level coupler and for the data assimilation. So generally, so coupler is a weak coupling of the multiple applications, and usually two applications, such as atmosphere, ocean, and structure and fluid. But this coupler is very sophisticated, and we are also connecting the different type of workload, simulations and AI workload. Okay. So another issue is these two parts are based on the very different architectures, and so it's impossible to run the single code using the MPI on these two systems. And we developed a communication library to connect these two parts. And this type of library is available since last year, June. Okay. So we utilize this type of the system. For example, one is a 3D architecture simulation with real-time data observation and assimilation. And so we are based on the real-time observational data to predict the earthquake simulation data. And another application is this type of the integration of the simulations and AI workload through this coupler using Odyssey and Aquarius. Okay, so this is one of the applications, and so this is a global cloud simulation. Okay, and in this type of the simulations, we use a very fine mesh model for the global simulations. And also we use such kind of the parameterization. Okay, so this model is rather coarse. Okay, but we need a lot of cases for this parameterization, and 75% is spent for this fine mesh, and 25% for the parameterization. Okay, so our motivation is trying to replace this part with AI. Okay, and so I skipped the detail here, but yeah, we try to predict the time gradient of the density and the internal energy and density of the vapor. Okay, and using a very simple 3-layer multi-layer perceptron. And so, yeah, this is the result, and this is the input, and this is the simulation result, and this is the prediction by machine learning. And we still have some problem for carrying the peak, but so basically
they provide a very good agreement with the simulations and machine learning. Okay. Okay, so this is a summary of our systems, and unfortunately, so we have a limited time, and this time we just use a very small part of the system. But yeah, you can use this type of system for this kind of purpose. And if you are interested in, so yeah, please contact me even after this school. Okay, so any question for this part? Okay, so now it's 2 o'clock. So let's take a break and so go back to the login to the system. Okay, so let's start. So we need a, so by the way, so how many of you have experienced the SSH login before? So you are, okay, several. Okay, so anyway, so let's start the SSH public key authentication. And it's a safer than the password authentication. And so yeah, generally, it's very widely used all over the world to log into the this type of system. So we have 4 procedures. Okay? And one is creating the keys, and another one is accessing the portal site, and the registration of the public key to the portal site, and log into the Odyssey by SSH. And creating keys so on your PC, and so private key and public key are so generated on your PC. So you need to enter passphrase. Okay, so it's a password for SSH public key authentication. And empty passphrase is prohibited. And please enter a certain kind of the passphrase. And if you have already created keys on your PC before, you can skip this process. And please make sure it is with passphrase. Okay. And the next one is accessing the portal site. And please so prepare your user ID and initial password with 8 characters. Okay. And so you are requested to change the password after accessing the portal site. So this passphrase and this password, so they are different, okay, and also separated. Okay, so please think about that. So there are several rules for number of characters or communication, etc. And please read the instruction carefully. Okay. And the third one is the registration of the public key to the portal site. And these 2 and 3 are essential, even if you have already had UIDs on Odyssey. And the last one is login to the Odyssey by SSH. Okay. Okay, so let's open your terminal. So how many of you are using iOS, Macintosh, Apple? No? Oh, 1. And how about Windows? Okay, so are you using WSL? Okay, so, and you are using, okay, Mac OS, okay, that's fine. Okay, so please go to the terminals of the Mac OS or so WSL. So type SSH minus keygem blank minus T blank RSA. Okay. And so you are asked the so location of the key. So please use the default one. So in that case, just return. Okay. And the next, you are asked to enter the passphrase. And please enter your passphrase. Okay. But please don't do the empty one. Okay. Then return. And you are asked so confirm that and the same passphrase and return. So this is the summarized procedures. And SSH keygen TRC return, just return your favorite passphrase return, same passphrase return. So these are the procedures. And yeah, probably you can find this type of some messages on your screen. And so, yeah, please complete this part. And please, so raise your hand or ask me if you have any problems. Can we go to the next part? Let's go to the next part. Okay, so this is the return. Okay. And please go to the cd blank /.ssh. So this is the location where the two keys are created. Okay. So one is a private key, ID RSA, and another one is the ID RSA.pub. And please confirm that these two are created. Okay. And the next thing is please type the cat blank ID RSA.pub. Then you can find this type of group of letters. Okay, starting from SSH RSA. And probably last one is so your system name of your PC, and this is the username on your PC. So please make sure this kind of information is created. Yeah, this is my private, my public key, and so of course it's different. Okay, so this part will be used for registration of the public key. And the easiest way is just copy and paste this part. And so what I would like you to do now is copy this part. Okay. And so starting from SSH RSA and to the end. And sometimes, so this part includes so-called multi-byte characters, such as a Chinese character. So because yeah, in Japan and China and Taiwan, so sometimes so their machine names could be so using Chinese characters. So in that case, you should avoid the last part. Otherwise, you can include all parts. Okay? So if they are just alphabet, and it's okay to include all things. But if you have include some multi-byte characters, please copy from here to here. Okay, okay, so just so copy to your memory of your PC. And also, please make sure the cursor should start from here to here, not from the end to the top. Sometimes it provides some accident. So start from here to here to scroll. Okay. Okay, so if it's let's connect to the portal side. And please prepare the two information. So actually, so it's on the your this paper. And the user ID is T17 something. And so, yeah, on the first line, so you have these two information. Another one is the initial password with 8 characters. And so you should prepare these information. Okay, so please connect to the portal site. And I think it's better to use English. And then you are asked to enter the user ID and password. And please enter your user ID and 8-character password, which is printed on your paper. Okay. And if you are successful with the login, so you are asked to change this password. Okay, and please change the password according to some rule. So there are some policies. Okay, and please read these policies carefully. Okay, and so you need to enter the current password, and so new password and another confirmation for the new password. Okay, so you need to enter new password twice. So if the new password is not based on the rule, so you are asked to do the process again. So in that case, you have to start from this one, okay? Entering the current password. And in order to reduce the work, so please carefully read this instruction. And of course, you should keep the new password and also the passphrase which you created, so in somewhere confidential. Okay? So in the case of the portal site, so login, so you can reset your password. Okay? But anyway, so please, so remember, keep. Okay, so let's go to the next part. And so you can find several menus here, and please select this SSH public key. And you can get this kind of window, okay? And so we have several methods. One is a direct input, and another one is file upload. And I recommend this direct input. It's a default one. And so please paste the ID rsa.pub on your PC, okay? Like this way, okay? And click register. And if it's successful, they say it's registered or something. And you can see that you are registered public keys in this window. Okay, so please do this. Okay, so please go to your terminal or your PC, and please type this. So SSH blank T17. So this is your ID. Okay, @ wisteria.cc.u Tokyo ACJP, and return. And at the first login, so you are asked to, so are you really, are you sure you want to continue connection? And type yes, so in the full spell, okay, and return. And after that, so you are asked enter the passphrase, okay, and please enter your passphrase and return. And if you are successful, so you are, so this is after the second login. And so you can get this type of the screen. Okay, okay, so please raise your hand if you have any problems. You log in, so you can get some information, some schedule for the operation. Okay, and generally speaking, in the last Friday of each month is a day for the maintenance. So you cannot access the system. So you can check this type of the information when you log into the system. And you can also find some information about some questioning part. But please don't access this website. So please contact me by email if you have any question. Okay, so I just show you some general rules for this type of the SSH public key authentication. Okay, so in first creating your keys on your PC. So one is a private key, and another one is a public key. And you register the public key. So you go into the portal site. Okay, and so you registered your public key, okay, to the this private key and public key is something like a key and lock. Okay, And so there's a pairs. And so if you send the information of the private key with passphrase, so they can so open the lock, which is the public key on the system. So this is a general operation. And IDRC is a private key on your PC. And keep it confidential. Okay? And for example, please do not give it to others, do not copy, or do not move, etc. And so hopefully, so you don't move from the location to other part. So if you create it once, okay? And the public key is on the supercomputers, and you can copy and can send it to others via email, etc. And also you can show it to others. Okay? And if the information of the private key on your PC and public key on the supercomputer matches, you can log in. And if you have multiple PCs, please create individual set of private key and public keys on each PC. And you can register multiple public keys on supercomputer. Okay? And so you are now created your own PC. But for example, if you have a desktop system on your laboratory or your home, so yeah, I recommend you to create another set of keys and register that from your systems. And actually, so this user ID is valid until the end of September. Okay, so almost more than 2 months. Okay, so you can review the materials. Okay, this is procedures, and yeah, please create another set of keys, and you can register. Okay. So for example, this is my page, and you can see I registered so 2 sets of the keys. And so in this case, the system find one of the matching keys. And if keys are matched in the one of these, it's okay. Like this. So after login, so PWD shows your current directory. So probably just after login, they show the home T17 your user ID. But generally, you should work in this work directory /work/DT17 and T17 your user ID. And if you type PWD, and it shows work GT17 T17 XYZ. So please use this directory, okay? Because you cannot compile or submitting the job from this home directory. And the capacity of this home directory is very small. And if you want to go back to the home directory, type CD and return. Then you can go back there. Okay. So this is how to copy the files from and to PC, so between PC and Wisteria Odyssey. Okay. I skipped the details, but basically you are using the SCP command. Okay. And actually, so you can so copy the whole directory if we are using this -R option. Okay, so this is a PC to supercomputer, and this one is a supercomputer to PC. Okay. Yeah, this kind of procedure is very important and useful if you want to visualize the result on the PC, on the supercomputer on your PC. And also you can access the manuals on the portal site. And if you click the documents, and so every time you click here, so this menu appears. Okay, because the manual is a very important document, and only users are allowed to access those. Okay, and you can download and make the copy for your usage. But after October, so please delete the files or shred the files. And please don't give it to others who are not the users of this system. Okay? So please keep this rule. So this is not a local rule. So this is a Japanese law. So please keep this. So anyway, so please keep statements. Okay? Yeah. Okay, so if you have any questions, please contact me via email. So do not contact the ITC support directly. And it is strictly prohibited to use our system for purposes other than this class. Okay? And also, you cannot use the Aquarius, so GPU part. And so please keep in mind. Okay, so any questions for this part? Okay, so yeah, we still have time. So let's go to the main part of the MPI. Okay, so this is an introduction to the programming by MPI for parallel finite element method. Just a moment. So this is the first part. Okay. So let's start by this page. And I have already mentioned several times. So this is the motivations for the parallel computing. And we need computing for large scale scientific computing. And I also talked about some scalability issues. Okay? One is weak scaling, and another one is strong scaling. So this is an overview of this part. And so this is a MPI part. So we start with what is MPI. And by the way, how many of you have already experienced MPI before? No? Ivan? So, okay, you also. Okay, so anyway, so your first MP programming, some of you are first experience. And after that, so we have two parts. One is the collective communication. So it's related to the dot product. Another one is a point-to-point communication. It's a communication for the matrix vector multiply. Okay, so MPI stands for the message passing interface. It's a specification of message passing API. So API stands for the application programming interface. It's a message passing API for distributed memory environment. So MPI itself is not a program, or it's not a library. So it just specifies a interface. Okay? And the implementation is up to the each library or runtime. And you can see some specification in this homepage. For example, this homepage is R1. So you can see, so this is a reference of the MPI functions. So actually, so even I don't remember the number, 400 or 400 or something, many functions. But so as I mentioned, we use very small part of these. Yes, yeah, less than 10. And so another part is, I think, more. Yeah, this is a MPI forum, and MPI forum. So this is the MPI specification. And then you can read some MPI documents. And the most recent one is the MPI 4. Yeah, this is the 4. Okay. And you can read the most recent specification on this part. So it's roughly 30 years old. And in 1992, so MPI 4 started. And then 94, so specification of the MPI was released. And so you can see, so every, so yeah, you can see between the MPI 2 and the MPI 3, you have a long time. And the MPI 4 is recently announced. And actually, in this class, we are so using just the MPI 1. Okay. And in MPI 2, we have MPI IO. And MPI 3 are for Trojan's or asynchronous collective so supported. But so in this class, we are mainly focusing on the MPI 1. So there are several very famous implementations. So one is MPI CH. It's by Argonne National Laboratory in USA. And OpenMPI and MPAPICH. So they are very famous implementation. And hardware vendors, so such as Hewlett-Packard or Intel, they developed their own MPI. Yeah, they are based on the so one of these MPICH or OpenMP or MPAPICH, they are open source library. And then they are so they can be used from C, C++, Fortran, Java, and also we have Python version recently. And I never used the Python version, but so it's also available now. And in many types of the operating system, Unix, Linux, Windows, and Mac OS. And so MPICH is a free version, and this is widely used. And so you can see the details on this homepage. So I think they are still working. Yes. Yeah, actually, so MPICH is developed by Argonne National Laboratory in USA. And this is one of the central institute which develops the MPI. Okay. So MPI is widely used as a de facto standard for the message passing, because it's a for example uniform interface to MPI forum. So MPI forum is a very active associations or consortium, and they still have a times meeting every year. Okay? And of course, in recent 3 or 4 years, they are fully online. But recently, they have a in-person meeting, and so it's very portable. Okay, and can work on any types of computers, and can be called from Fortran and C and etc. And I believe that MPICH is a very big contribution to that. Okay? It's free and it supports every architecture. And every time, so if you have a new architecture, so MPICH, catches up that most recent architectures. So I believe, yeah, it is one of the very contributions to the this situation of MPI. There's another parallel library or parallel environment game. It's a parallel virtual machine. So that was also proposed in early 90s. It's not so widely used as MPI because they don't have any MPI forum type consortium. And the MPI forum consists of the universities and national laboratories and also vendors. Okay? And also vendors with IBM or Hewlett-Packard or Hitachi, Fujitsu, or Intel, or something like that. So there are several references, and actually, you don't need to read these books. And so if you want to read books, so there are several so references like this. Okay, so next I'd like to talk about some how to run MPI. Okay, so this is not a language, but you need to know the rule, okay, to make a program. That means so you need to learn grammar. Okay, yeah, it's same as a usual programming language. And but as I mentioned, so we have so over hundreds of the functions in MPI, but you just need to the function of MPI one. Okay, so these are in this class. And if you further information, so you can find information from website and MPI expert. And practice is very important. Okay, and this is the programming. And also, you can start from the running the code. Okay. And you should be familiar with or grab idea of SPMD or SIMD operations, which I showed this morning. Yeah, this picture. Okay. Oops. And a single program and multiple data, and each process does the same operations for different data. And large scale data is decomposed, and each part is completed by each process. And global data and local data, and global numbering and local numbering. So I have already so about this part, global and local data and numbering. And this part is very important. So actually, so correlation or designing of the local data is very important for the parallel computing, and the numbering is so the starting point for that. Okay, and some physical terms. Actually, so this, I prepared this material nearly 10 years ago. Okay, and in recent 10 years. So the technologies, so the advancement was so fast. So that means so we have been using the different technical terms. Okay, and actually, so I still keep the very old terms. Okay, so one of these is this P. Okay, P is a very so convenient word. And I'm using this word in this material. So actually, EE itself is not so in the current community. Okay? Yeah, all the guys like me still use P, but yeah, probably young people don't use PE, or they even don't know what does PE mean. But anyway, so PE is very convenient word, and I sometimes use this. Okay, processor core. So there's a processing unit, and it's a hardware. And in the case of single core process, so it's a processor is equal to core. But now the processor consists of the multiple cores. Okay, process is a unit for MPI computations and nearly equal to core. Each core or each processor can hold multiple processes, but not efficient. Okay? P is a so stands for the processing element, and the PE originally means processor, but it is sometimes used as a process in this class. Okay? Moreover, it means domain in the next part. And in multi-core processors, PE generally means core. So domain is a more so application side term. So by the finite element or something like that. And the domain is so identical with the process, and also it's similar to PE. Okay, and each of the in the SPMD is corresponding to this domain for each data set. Okay, so sometimes these words are used in this material without any detailed explanation. Okay, so yeah, I will explain that if I need. Yeah. Anyway, so there are several this type of words. Yeah, again, SPMD. Okay, so how to run MPI? And so actually, it's not so difficult. Therefore, 5 or 4 hour lectures are enough for just learning grammar of MPI. And so important point is grab the idea of SPMD. Okay. I think we spent this afternoon and tomorrow. So yeah, probably I will spend for MPI. Okay. And we have some exercises, and yeah, probably that's enough. So we will have very small issues. Okay. Small number of functions. Okay, so this is a schedule, and starting from the basic functions of MPI and collective communications and point-to-point communications. And so now the University of Tokyo usual lecture time is 105 minutes. Okay? 1 hour and 45 minutes. But it was 95 minutes, 90 minutes before. And so I needed so 4 or 5 slots for the 90 minutes. Okay? And then we have some homeworks, exercise. Okay? And one is a collective communication. It's a very simple one. And the second one is about the parallelization of the 1D code. Okay? And so the last slot, I asked you to this homework. And if you finished these two, so you are an expert of MPI programming. Okay. Okay, so this is a A64 FX processor on Odyssey, which you are using, which you are using now. Okay. And we have 48 cores, and each node includes 4 CMGs. So CMG stands for the core memory group. And so each CMG has a local memory. So this HBM2 is a memory. And so 12 cores on each CMG. And it's a 2.2 gigahertz and 32 double precision in a cycle. And we have 48 cores. And the total performance of each node is 3.38 teraflops. It's a very fast system. Okay? And it's a NUMA architecture, non-uniform memory access. And each core of the CMG can access to the memory on the remote CMGs. The utilization of the local memory is more efficient. And multiple nodes, if you use the multiple nodes, recommended program model is a 1 MP process for each CMG with 12 OpenMP threads. Okay? And 4 MPI processes for each node. Okay, so we start from the single MPI process for each core, but in the last day, probably Friday, so we are switching to the hybrid of the OpenMP and MPI and apply this type of the parallel programming model. One of the feature of the this architecture is that this memory is embedded on the chip. Okay, so yeah, because it's very high bandwidth, high memory bandwidth, but the problem is that the capacity is very small, and you can see total memory size for each node is just 32 gigabyte. Okay, So generally speaking, on the Xeon type processors, they have a so at least 128 gigabyte or so 256 or something. But compared to that, it's very small. But it's very, very fast. Okay. Okay, so this is a overview. And this is a ID of each component of this part. So CMG's ID is starting with 0, 1, 2. And the memory ID is starting from 4, 5, 6, 7. And ID of the core is starting from, okay, 12 to 23, 24 to 36. And the last one is a 59, okay? So this means CMG, memory, and cores don't share the same number. Okay, so I think it's so for avoiding the confusion. Okay, so anyway, so you may have a chance to utilize these numbers. Okay, any questions so far? Okay, so I think it's good time to stop here and take a 10-minute break. So it's okay, so it's time. So let's start the real programming part. Okay. Okay, so first of all, please log in again to the Odyssey. And so please go to the directory at this work GT17 and T17, your user ID. And please make directory pfm. So the name is so up to you, and but this name is yeah, it's very easy to understand. And every time you log in, please type module blank load blank fj, because so this is loading the compiler of the Fujitsu's related. Okay, because Odyssey consists of the two types of node, and so another is the GPU cluster, and they provide very various types of the environment: Intel, NVIDIA, AMD, or something like that. And so we need to use a different environment. And if you use the Odyssey, yeah, please don't forget to type module blank load blank fj. So every time you log in, yeah, if you type this once, it's okay. Okay. Then please copy the files from my directory. Yeah. Okay, so please go to the pfm and type module load fj, and copy work GT00 Z30088 pfm. So this is the Fortran case, and this is the C case. And so please don't forget this blank dot. Okay, if you forget this dot, you cannot copy. Okay, so this dot provides a destination, for the copy. And after copy this file, please type tar blank xvf blank s1 minus f dot tar or s1 minus c dot tar. And you can find the directory MPI underneath that. And please go to the MPI S1 directory. Okay, so yeah, you can find this MPI S1 directory. Okay, so please copy my files to your directory, and so yeah, extract the files. So please, yeah, for me if you have any. So I think a permission is okay. Okay. So if you can enter the S1 directory, so yeah, please don't forget it. Then the first example is hello.f and hello.c. Okay, and generally, if you run the programming language, so first thing is putting the hello or hello world on the screen. Okay, so this is an MPI version for both of the Fortran and C. Okay, so basically, the main part is this right hello world Fortran and this hello world. And you can see, so they are calling several MPI functions starting from MPI. Okay, so MPI init, comsize, comrank, and finalize. So this is the C part, and they are also calling the same name of the function. Of course, the interface is a little bit different. Okay, so yeah, please compile the hello.f or hello.c. Okay, so this is how to do that on the Fortran case. And if you are C users, so please type MPI FCCPX blank minus NC lang blank minus kfast hello.c. Okay? So please type this way. So this MPI FCCPX provides some compiler environment, also the required libraries. Okay? And so which is used for the Fujitsu's C plus MPI. For MPI FCCPX minus NC lang. Okay, so if you are successful, you can find a.r. Yeah, before going to the next part, so I talk about this NC lang option. Actually, several compilers are available. So especially in the case of the C, so we have two modes. One is a TRAD mode, and another one is a Clang mode. Okay, so TRAD mode is based on the Fujitsu's compiler developed for K and so successors. Okay, and compatible with the Fujitsu's traditional compilers. Okay, and this is a default. Okay, but generally slow for the material in this class, and so I recommend to use this Clang. Okay. Clang is based on the open source compilers for ARM architectures. And actually, so it supports a little bit higher version of the OpenMP and generally faster than TRAD modes. Okay. And so in this class, I recommend you to use a Clang mode. Okay. So in order to use Clang mode, you need to make this option explicitly minus N Clang. Okay. And if you don't do this, so yeah, you just use that. Or you can specify the N no Clang. Okay. But this is default. Yeah, basically, in the case of the hello.c, yeah, it makes no difference. But in the later case, so you may have some effects. Of course, you can compare these two, but so yeah, at this stage, I recommend you to use NCLAN. So that's why. So I put NCLAN here. Okay. So if you are successful with the compiling, so next thing is run the job. Okay. So it's different from the PCs or your cluster in your laboratory. So it's only so allowed for the batch jobs. Okay? Interactive jobs are also possible, but so educational users, such as like this users, are not allowed to do that. So how to run is starting for the writing the job script, submitting job, checking job status, and checking result. And one node, 48 cores, is occupied by each job. So even if you use a single core on the node, the whole node is occupied by yourself. So it's not shared by other users. Okay, so this is a hello.sh, and this is a very typical job script. And this provides information about the scheduling and the shell script. And so, yeah, we need to so modify the files on your directory because so we need to use the update, up-to-date so information. Okay, so this one is a resource group, and so this is the name of the resource group which we can use. Okay, and you need to specify the proper resource group. So in the case of the educational users, it's very limited. And the resource group should be lecture 7.0 or lecture 0. Okay, so I'll talk about explain about the lecture 7.0 and lecture 0. But so currently, so you can specify lecture 7.0. So next two lines shows a node number and number of MPI processes. Okay, and in this case, we are using a single node, and the process number is 4. Okay? And we have 48 cores on each node, but in this case, only 4 cores are used. So next part is elapse is so computation time, and in your case, so educational users, the 15 minutes is so upper limit. Okay? So actually, so this work doesn't take so long time, but 15 minutes is upper limit. So this is the hour, this is a minute, and this is second. And another important information is GT17. So GT17 is a group name, and so your user ID is starting from T17 something, and it's related to this group name. And also this 7 is taken from this cell. Okay, so anyway, so this one and this one should be modified from the file on your directory. And this is the standard error output, and this is the standard output for output list. So you can change the name of the files. And also this module load FJ and the module load FJ MPI it's essential. Okay? So every time you run the code, please insert these. And the MPI exec is running the MPI jobs. So using these resources, and this is the name of the load module, executable file, ./a.out. Okay? The name of the file is a.out, but please don't forget /. Okay? Okay, so let's run the code. So please modify your shell script. Please open the hello.sh. Okay, so I'm going to say can you modify the vector and the vector also is okay? So this 87 is all the stuff. Yeah, this time, so we need to expect to give two parts. So resource group and group name. Okay? And if you want to submit the job, you just submit this row. Okay? So if you type pjstat, so I'll talk about this later, but the pjstat provides your the status or your event. So now it runs. So if you have something or nothing, that means you are having. And you can find hello.list. Hello.list is PH. And you can find so hello.list. Okay, so hello was 0, 3, 1, 2. So the number integer is corresponding to the process ID. Because we are running the 4 MPI job here. And the process ID is starting with 0, 3. So each number is corresponding. The sequence could be changed. But, if you get this kind of the output, so it's happens. And each line was written from the each MPI prompt. Okay? And it's separate. Okay. Any problems for this part? Are you okay with this? Okay. Well, actually, so you can change the number. So because in this class, you can use up to nodes, okay? And so that means so you can use up to 576 cores, okay? And this is a node, and this is a MPI block. And so you can use up to 48 MPI processes on each node, okay? And so and also this so yeah, you can increase the number of nodes 4, 8, 12, and up to so 576. Okay, so this is so how you use that. So you have already submit the code like this way. So these are the available resource groups. Okay, and so actually, so following two resource groups are available. So up to 12 nodes are available. So one is a lecture O, and another one is a lecture 7O. So in each case, you can use up to 12 nodes and 576 cores. And the upper limit of the job time is just 15 minutes. Okay? And so actually, during this week, 95, yeah, you should be, it's recommended to use lecture 7O because more resources are so assigned during this lecture. But so other times before 9 o'clock or after 5 o'clock or after this school next week, so you should use lecture O. Okay, so it's valid until the end of it says August, but it's until the end of September. Okay, but it's shared by all educational users, and sometimes it's a little bit crowded. You may have to wait for a while, but it's not so bad. So these are some commands for submitting and checking jobs. And you have already done this at PJSub, and the PJSub script name is submitting the job. And if you type the PJStat, you can check the status of the jobs. And also you can delete the jobs by PJ blank job ID. And if you have additional parameters, you can see some information from this PJ stat. I'll show you some examples in the next several pages. Okay, so for example, so you are running the FT f248.sh and f348.sh. And if you type PJ stat, so you can find two of your jobs. One is running and one is queued. So queue means so it's waiting. Okay? But after several seconds, if you type PJ stat again, so both are running. Okay? And so you find something wrong, so something mistake in the second jobs, and you can delete the second job. So job ID is displayed here, and this number should be entered. PJ blank the job number, and so it says that it's accepted. If we use many nodes, for example, more than 500 nodes, it takes a while. But in the case of a single node, it stops very immediately. And you can see if you type PJ stat, and you can see, so this second one is already deleted. And so after several seconds, so if you type PJ stat, so there are nothing in this part. So that means, so this is also finished. Yeah? So this is how we utilize PJ stat and PJ del. And if you apply some options, you can get some information about your jobs and also your resource group. For example, so if you type PJ stat minus blank minus RSC, so you can get the information about your available resource groups. Enable start means that it's so you can use this. But disable stop means that you cannot use that. Okay. So probably if you type this now, both are enable start. But after 5 o'clock, so yeah, probably lecture 7 or will be disabled stop. Yeah, this is very convenient. And so actually, after 5 o'clock today, so if you submit the job to the lecture 7.0, the job will start tomorrow morning, 9 o'clock. Okay? So yeah, please be careful about that. And also, they can provide some maximum number of the usage. So you can check the maximum time or maximum number of nodes by minus RAC blank minus X. Okay, thus you can get some information about your resource group. Okay, so this is a very fundamental information about the usage of the system. So any questions so far? Okay. Okay, so let's go inside the program. So actually, it's a very simple program, but I will show you what it's doing here. So this one is a hello.f, and this one is a hello.t. And you can see, including the MPI f.h and MPI.h. Okay, so these are the essential include file. Okay, so these includes some environmental parameters, and if you are using MPI, so you have to include these files. In the case of the Fortran, you can apply use MPI, so instead of include MPI f.h. So basically, we are calling 4 functions: MPI init, MPI com size, MPI com rank, and MPI finalize. Okay. And MPI init is the initialization, and MPI finalize, the termination of the MPI processes. And these two are essential. Okay? And the MPI com size is so they get the number of MPI processes. And the MPI com rank is a process ID for each process. It's starting from 0. So these two are not essential, but it's better to call every time if you run the MPI code to check the status of the program. So this slide describes the difference between Fortran and C. So basically, they are same interface. But in the C language, upper and lower cases are considered as different. Okay? And in the case, Fortran case, there are no difference. Okay? So this means in the case of the C, some of the capitals and the lowercase are strictly defined. Okay? And the name of the function of the MPI must be, so MPI must be capital, and the first letter after MPI underscore must be capital, but others are lowercase. Okay, so this is a rule. And in the Fortran, return value is just a moment. In Fortran, return value IRA has to be added at the end of other argument list. Okay? So Fortran must be usually has more arguments compared to the C language. So C means special types of variables, and so actually current Fortran interface is very close to C, but we have some special variables, MPI con, MPI data type, or MPI operation, etc. And the MPI init is different. In the case of the Fortran, we have only error code. But in the case of the MPI in the C language, please just specify these two. Okay, so every time. So that's the difference. Okay, so let's see what's going on in this hello. So this is the hello.c. Okay. Okay, so you can find this MPI exec in the shell script, and we have a single node, and we have 4 MPI processes. So MPI exec starts up 4 MPI processes because proc equals 4. A single program runs on 4 processes, and each process writes a value of my ID. Okay, so in this case, it's a my ID. So my ID is getting from this MPI com rank. It's a rank ID, and this my ID is written in with a hello world. Okay, and the 4 processes do the same operations. Values of my IDs are of course different. Okay, so output of each process is different. And so as I mentioned, so each line is written by each MPI process. And this is very primitive, but this is a very typical SPMD operations. Okay, and so they are doing the same things. So they are running the same program, but the data, my ID, is different. Okay, so that's a kind of SPMD operation. Okay. So MPI.h and MPI.f.h, and various types of parameters and variables for MPI, and their initial values are defined. And the name of each variables starts from MPI underscore. And the values of these parameters and variables cannot be changed by users. And I recommend not to use the name starting variable name starting from MPI underscore. Okay, and if you want to use this type of name, for example, I recommend you to do the my MPI underscore something. Okay? So anyway, so please avoid the name. Yeah, because we have a lot of such variables. Okay. Okay, so MPI init. So it initializes so MPI execution environment. So it's a required, essential. And so if you read the textbook, it says this statement must be in the so beginning part of the MPI procedures. But I recommend this all statement in the program. So if you use MPI, okay? So it's better. And the next one is the MPI finalize, last one. And it terminates MPI execution environment. So it's also essential. And so, yeah, it is recommended after all statements in the program, okay, if you use MPI. And please do not forget this, okay? And if you forget this, process doesn't terminate, even if the job is terminated, okay? And in the case of the supercomputers, it's okay. But if you are using the some your local PC cluster, it has some problems, okay? And please don't forget MPI finalize. Okay, so next one is the MPI common size. And it's not so essential function, but it's recommended, okay? So determines the size of the group associated with a communicator, okay? And we have two arguments. One is a so communicator, and this is a type. Type is a MPI com. And another one is a size. Size is a number of the processes in the group of communicator. And this is a so integer. Okay, so this is input, and this is the output. And this shows the MPI com size, and this is the name of the communicator, and this is a total number of processes. So in this case, it's 4. And you can get the so number of processes from this function. Okay, so what is communicator? Okay, and the communicator is a group of processes for communication. And the communicator must be specified in MPI program as a unit of communication. And all processes belong to a group named MPI com word, so all capitals. So this is a default, okay? And multiple communicators can be created, and complicated operations are possible. For example, you can make a communicator for computation and visualization. But in this class, basically we are using just MPI com word, okay? And so MPI com word includes all processes in this program, okay? And so, yes. Yeah, for example, you can divide the MPI processes in so 3 communicators, okay? So this is some so mantle convection and class deformation and visualization. So you can utilize this type of the so models. Actually, so many years ago, almost 2 years ago, I developed so some applications about related to multiple communicators. It's a coupling between ground motion here and the sloshing of the tanks for oil storage. So this is a one-way coupling from ground motion to tanks. So this is some earthquake phenomena, and this so motion is transferred to the tank, and so the tank is so sloshed. So in this case, so this part, ground motion part is so divided into some parallel finite element method. And the tank is also finite element method, but each tank has a single process. And the motivation of this application is a 2003 earthquake. It's a magnitude 8 point. So it's a very large earthquake. It's a 2 years ago. Okay? You can see, so this is the island of Hokkaido. I heard Hokkaido is a very popular place in Taiwan. So yeah, some years ago, I saw some television program and in Taiwan, and so people in Taiwan were discussing about how the Hokkaido is a very nice place. Yeah, I like Hokkaido, but I'm very curious about that. But anyway, so we have a very big earthquake, and this is the epicenter, and this is the city of Tomakomai, and it's almost 300 kilometers away from the epicenter. So this area is called Tokachi. Okay? But that city is very far from the epicenter. So Tomakomai is a very famous industrial city, and they have many tanks for oil storage. And the oil tanks in Tomakomai shook violently by the earthquake. And the sparks with a rubbed metal fitting ignited the oil that swung on the liquid level. The fire was so large that it was impossible to extinguish it. And we needed to wait a few days for all the oil to burn out. Okay, so at that time, that is a very big fire. And we cannot stop that. Okay? And just wait for 2 or 3 days. Was all the oil were blown out. So at that time, the damage by the earthquake was not so significant. I remember, so this fire accident was very terrible. Last year, so I went to the Hokkaido, okay, so in September. And this is the flight between the Sapporo and Tokyo. And actually, city of Tomakomai is on the way to the Sapporo. And you can see this type of the oil tanks. So there are still many oil tanks in this city. Okay, so I just talk about some background. Yeah? As you know, seismic wave includes the various components of wavelengths. Okay? And so if you make some spectral analysis, so you have a very different spectral property for the several earthquakes. Okay? So Niigata 2004, Kobe 1995, and Tokachi 2003. And this provides some peak period. If it's short, period is very small, and if it's large, period is very large. So you can see, peak period is very different for each earthquakes. So buildings with the same natural period as a predominant component of the seismic wave shake most violently. So it's a kind of the resonance. Okay? And long period waves last long and reach far. And long period waves shakes the large buildings. The contrast. So short period waves shakes the small structures. And unfortunately, such earthquakes is with a very long period waves. So that's why this type of the big structure was shaken violently. Okay? Yeah, this is a very interesting phenomenon. And we developed the code, and we are mainly focusing on this very shallow part. And so some basement and also some building. So this is an overview of the code. And you can see ground motion part is so finite element and written in Fortran. And this tank part is so this is also the finite element, but it's written in C language. Okay, so actually connecting C and Fortran programming is very easy for the OPI. And so now the interface between C and Fortran is very easy, but at that time not so easy. But MPI provides a very nice interface between language. And in that case, we created 3 communicators, whole things, just for tanks and just for so basement. Okay, so this is the coupling between ground motion and sloshing of the tanks for oil storage. So wave is coming from this way and propagating in this direction. And I thought this color means some deformation in the direction of the seismic wave. Okay, so this is a video, and you can see. So we have some sloshing and so deformation on the oil surface like this way. Okay. Yeah, so this is a definition of the MPI ComWord and the communicator. Okay. And the next function is MPI ComRank, and it is the rank of the calling process in the communicator. So this is the ID of MPI process, is sometimes called rank. And in this case, you need to specify the communicator, and you can get the rank ID starting from 0. So in this case, so the rank ID is written in this my ID, and this my ID is written with a hello world. Okay. Okay, so I'll show you another function. So generally we don't use a lot. So MPI abort is the abort MPI executed environment, and so you can specify the communicator and error code. Okay, and usually we don't use this. And if you want to do some debugging, we use this MPI abort. So MPI double time is very convenient for measuring the time. Okay, so return as an elapsed time on the calling processor, and this is a double pressure. Okay, usually we put time equal MPI W time. So generally speaking, so we the MPI W time twice. And if you take the difference between E time and S time, so you can measure the time between these 2 statements. So this is a very typical way to utilize this function. Okay, so I think you can find some examples of the MPI W time. So this is a MPI GT 27, it's a 17. Okay. Sorry. Yeah, you can measure the time. Actually, if you apply the minus K fast, it's too fast, and you cannot measure the time. So I just put the lower level of the optimization. Then you can measure the time for the you can see it's almost same. Yeah. And so this one is go4.sh, and this is running the 4 processes. Okay, it's almost same as hello.sh. Okay, but the output name is a test.list. Okay. And the MPI double tick, so it returns the resolution of the MPI double time. And it depends on the compiler and the hardware. And in the case of the Odyssey, it's order of the microsecond. Okay, and you can so measure the time so as small as to the minus 6 seconds. Okay, and you can see so yeah, you just so the NPI is a tool, and you can write them this way. And I also have a sample code for MPI WT, and if you are interested in, so you can try that later. So in this case, just with a single process, and you can run the command.sh. Okay, the command.sh is so single node, but so you can see the process number is equal to 1. And another function is MPI boolean. Okay, so it works until all processors in the communicator have reached this routine. Okay, so mainly for debugging, and it's a huge overhead, and it's not recommended for real code. Okay. So this means so it stops. Okay, it is blocks all processes, and all processes are reaching this part. So we are going the next part. Okay. So yeah, it's mainly for debugging. Okay. Okay. Any questions so far? So I think I don't know that. Just check the schedule today. And today's schedule is okay. So I think our schedule is so the last so slot is exercise. Okay. And I think okay. So we still have so several minutes, and I just go into the introduction part of the collective communication. Okay, so far we learned about the very fundamental function about so MPI, but the next part is so collective communication, where all the processes in the communicator so joins for the communication, okay, such as a dot product. Sometimes it's called group communication, but collective communication is a more technical word. Okay? And collective communication is a process of exchanging information between multiple interfaces in the communicator, one-to-one or all-to-all communications. So examples are broadcasting control data, maximum, minimum, summation, dot product of vectors, and transformation of dense matrices. So there are some functions: broadcast, scatter, gather. Okay, and this P stands for the some process, and in this case we have 4 processes. Okay, and these A, B, C, D is so corresponding so to the some components of the vector. Okay, so broadcast means so yeah, one data is on this process. Usually it's on the number 0. And they just broadcast to other processes. And so each process has the same copy. Okay? So scatter and gather is a very interesting one. And scatter is just cutting the part in so several parts. In this case, in 4 parts. And they are so scattered to these 4 processes. So gathering is so this distributed data are so gathered into a single process. So this is a scatter and gather. So next one is a reduce and all reduce. And reduce is doing some types of the computations such as dot product. And so it's a reduction. Okay. And we have this type of vectors on each process. And in the case of the reduce, so all the results are gathered into the process 0. Okay? But in the case of the all reduce, it's a combination of the reduce and broadcast, and all the processes have the same copy of the result. So I'll talk about the reduction part in the probably tomorrow. And so there's also a function of the combination of the reduce and scatter. Actually, so I have never used this. Okay. Oops. I forgot to take this one. All gather is gathering the information and copy the all things. Okay, and all to all is something like the transpose. Okay, you can see this one is a transpose in this way, and this type of the function is used FFT, fast Fourier transform. But as you know, fast Fourier transform is not so efficient in the very massively parallel environment. And so I heard that it's not so used in recent days for very large scale computations. Okay. Okay, so I think this is a good point to stop. And so tomorrow, I start from the some samples by collective communication. Okay, so we have 4 types of the examples: product, scatter, gather, and reading the data bit file, and API or gather free. Okay. And tomorrow's schedule is just okay. So I think first 2 rounds I have some lectures, and exercise part is doing some exercise, and so the practice part I'll explain about some result of the exercise. Okay, I give you some assignment. It's a very simple problem. And after that, so this part is corresponding to the communications. And we have a little bit of large assignment here. And so on Thursday, so these 2 slots are optional exercise because I have some meeting here, so I cannot be here. And please do the exercise, or you can join the class after 11 o'clock. Okay. Okay, so this is a current schedules, and I hope so now everything is going well. And so any questions so far? So I will stay until 5 o'clock, and of course you can leave, or well, you can stay and do some exercises. Okay, thank you very much, and so see you tomorrow.